Welcome back to another lecture on chemical bonding. This lecture is on covalent bonding, and it's in your textbook, pages 22 through 27. By the end of this lecture, you'll be able to describe how molecular compounds are formed. You should be able to relate valence electrons to covalent bonding, and you'll be able to draw Lewis structures of molecular compounds. So molecular compounds involve covalent bonding. They are compounds that consist of only nonmetal atoms, and for nonmetal atoms, they always have 4 or more valence electrons, so it's easier to fill a valence energy level by gaining electrons. So when two nonmetals collide, the valence electrons are not going to be transferred. When a metal and a nonmetal collide, electrons are transferred from a metal to a nonmetal. With nonmetals, nobody's going to give up electrons because both of them are close to having a full valence shell already. So instead what they do is they share the electrons in such a way that both can achieve a stable octet. And electrons that are shared between two elements count towards both of their valence electron levels being full. The net compound charge is still going to be 0. No ions are formed in covalent bonding. And the covalent bonding is shown using something called Lewis structures. So we're only going to be looking at the atoms that are shown here on the left, those group 14 through 17 atoms. But they can bond to each other in a variety of ways. So here's an example of what we're talking about. Here we have one carbon atom bonded to one hydrogen and 3 chlorines. So the way it would look is if we take a look at carbon, if it's bonded to a hydrogen, this is the way the compound's going to look. So they're going to share 2 electrons. Now chlorine needs 8 to be stable. And carbon, so 3 chlorines. So this is the Lewis structure for trichloromethane, or chloroform. And if we take a look, all of the valence electrons are still shown. Notice that everything is clumped together, whereas for ionic compounds, the ions were actually separate entities with a charge on them. If we take a look around this atom here, you'll see that there are 8 electrons. So it's happy, it has a stable valence energy level. Carbon has its 8 electrons, again a stable valence energy level. This chlorine has 8 electrons, and this chlorine has 8 electrons. So notice that the electrons around the carbon are being counted twice in terms of valence energy levels. Hydrogen can get away with having 2 electrons in its valence because it only has that first energy level. So electrons can be counted more than once in terms of do they fill an atom's valence energy level. So here, 2 hydrogen atoms bonded to 1 oxygen atom, the most abundant molecule on Earth. So we have 2 hydrogens bonded to an oxygen, so I'll draw the oxygen first. It's going to have 8 valence electrons. And the hydrogens, and we can put it on any of the 2 sides. Hydrogens only need 2 electrons to be in full valence, so that hydrogen is a happy hydrogen. That hydrogen is a happy hydrogen. And of course our oxygen has 8 electrons around it. So this would be the Lewis structure, and we don't need the circles on it for the Lewis structure, so I'll draw it one more time. And so it doesn't matter what sides you put the H's on, but that would be the structure of H2O, water. So 2 bromine atoms bonded together, all halogens form similar bonds when in their elemental forms. What we have here is the diatomic element, Br, and it's bonded to another bromine. And again, they have to have 8 electrons around each of them. The 2 in the middle are counted twice in terms of determining if they have full. So both of these bromines have 8 electrons around them. They're stable. Their valence energy level is full. So, and the way this is going to work is we've been drawing the complete structures. If we take a look, here's an example of 2 hydrogen atoms that are freely floating around through the air. They bump into each other. Now, neither of them at this point has a full valence energy level. When they collide, they're able to share electrons. So when they collide, each of them gets those 2 valence electrons, and so each of them is going to become more stable by sharing the electrons. Same thing can happen with, here's an example with chlorine gas. Chlorine, in its elemental form, has only 7 valence electrons. So when 2 of them bump into each other, they can say, hey, I can share this electron here, I can share this electron here. When they do that, they both end up with 8 electrons in their valence energy level. So the 2 electrons in the middle count towards both of their valence energy levels. They belong to both of the atoms. So that's how covalent bonds are formed. So covalent bonds are the sharing of electrons in order to fill the valence energy level. It occurs between 2 nonmetals. So in this case, if you take a look at the nitrogen trioxide, there are 3 covalent bonds. If you take a look at chloromethane, there are 4 covalent bonds. Now, different colors were used for the electrons just so we could tell which one was coming from which element. You don't have to do that. That's strictly just for illustration's sake. The results are a molecular compound, and the electron dot diagrams for molecular compounds are called Lewis structures, mostly because a guy named Lewis invented them. So each atom in a molecular compound, except for hydrogen and helium, will always have 8 valence electrons. And atoms will share more than one pair if they have to in order to have those 8 valence electrons. Once you've decided on your Lewis structure, it's a good idea just to go around each of the atoms in it and just check. Make sure that each one has 8 electrons around it, unless it's a hydrogen, in which case it's only going to have 2. So for multiple covalent bonds, if we take a look at something like this structure here. Now here, carbon had 4 valence electrons, an oxygen bonded to one, an oxygen bonded to another one, and then hydrogen bonded to a third. But if we take a look, this carbon isn't stable. Neither is this oxygen, because these lonely little bonding electrons aren't being shared. We have an orbital for each of these atoms that isn't full. So what they're going to do is they're going to share more than one set of electrons. So by sharing another set of electrons, so if oxygen shares its electron with carbon, carbon gains one more, it'll have 8. If carbon shares its electron, then oxygen will also gain one more, it'll have 8. And so what you end up with is a situation where you have what's called a multiple bond, or you end up sharing more than one set of electrons. So here, oxygen and carbon are sharing 4 electrons, 2 from each, and this way they each have 8 electrons in their valence orbital. So if we take a look at oxygen, 1, 2, 3, 4, 5, 6, 7, 8. So those 8 electrons count towards its orbital. Carbon has a similar situation where the 4 that are being shared, and it has 4 more that are being shared with other atoms. So that is now a more stable structure. This is actually the structure of methanoic acid. So for predicting simple Lewis structures, we can follow a set of rules. The first thing we're going to do is determine the total number of valence electrons for the molecule, or the polyatomic ion. And it turns out that when we look at polyatomic ions, they're actually molecular structures that then bind themselves ionically to a metal or a nonmetal. Once you're done counting up those electrons, you're going to draw the Lewis structure for each atom in the molecule just to see what it looks like. And what you're looking for is unpaired electrons. Where you see unpaired electrons are potential spots for bonding. Paired electrons generally don't allow for bonding. The atom with the most unpaired electrons, or the one with the biggest electron deficit, is going to be what is going to be your central atom. Things are going to be bonding to it. So it's based on electron deficit. You bond to it the atom with the next most unpaired electrons, and so on until you have all the atoms that you need in your structure. Once you have that, you're going to go around and check to make sure all electrons are paired and that each atom is surrounded by an octet. If your central atom does not have 8 valence electrons around it, then that means it's going to have at least one bonding electron left freely around it. It's going to try and form double or triple bonds with neighboring atoms to try and fill up its octet. So, Lewis structure for nitrogen gas. So for this one, the first thing we're going to do is count the electrons. We have 2 nitrogen atoms. In terms of valence electrons, that means we have 2 times nitrogen's in group 15, so it has 5 valence electrons, so we need a total of 10 electrons. The only atom that we have is nitrogen. We just happen to have 2 of them, and this is what nitrogen looks like. Since we have 2 nitrogens, they both have the same electron deficit, so we're going to choose one. We're going to write that down, and it's going to be bonded to another nitrogen, and we'll put a bonding pair in there. And now we'll fill in the rest of our electrons. We only have 2 atoms. They can only be bonded in one spot. So now we'll fill in our other 10 electrons. So we have 2 so far. And so 3, 4, 5, 6, 7, 8. And we always fill empty orbitals first. And then after we add our 8, we still need 2 more. So 2 more of these orbitals, or 2 of these orbitals are going to have another electron. And once one atom gets one, you want to give one to another atom as well. So here we have our 10. And now we go around and take a look. We have our 10 electrons, so we can't add any more electrons. But we don't have octets around our nitrogens. Each nitrogen right now has only 1, 2, 3, 4, 5, 6 electrons each. Which means they're not stable. So now what they're going to do is they're going to start sharing more of their electrons. So these 2 electrons can be shared to form a bond, and these 2 electrons can be shared to form a bond. And when we do that, we end up with a structure that looks more like this. So now they're sharing 6 electrons, so we just line them up into 3 pairs, and there we go. And now this nitrogen has 8 valence electrons because it's sharing all 6 of those, so it gets to count all 6 towards its valence shell. And this nitrogen also has 6 valence electrons. So the Lewis structure for nitrogen gas would be this triple bonded structure. Again, you wouldn't draw the circles. If you want to draw it to kind of represent that extra repulsive force, you could put your lone pairs on the ends of the molecule, and that's something that looks like that. So there's your Lewis structure for a nitrogen gas. For hydrogen cyanide, so here we have 3 separate atoms, and we'll just go through our list. We have 1 hydrogen plus 1 carbon plus 1 nitrogen. In terms of electrons, that means we have 1 times 1 electron from the hydrogen plus 1 times 4 valence electrons from the carbon plus 1 times 5 valence electrons from the nitrogen. Again, we're going to end up with 10 electrons. And now we'll just draw our atoms. We have carbon, we have nitrogen, and we have hydrogen. Now the atom that's most electron deficit would be carbon. It needs 4. Nitrogen only needs 3 electrons, and hydrogen needs only 1. Remember, hydrogen can only have 2 electrons in its valence orbital because it only has that first energy level for electrons. So the most deficient is carbon. It's going to be our central atom, and we're going to bond nitrogen to it and hydrogen to it. And bonds are represented by a pair of electrons. So there we go. We just bond our extra atoms around our center, and now we got to fill in the rest of our electrons. Now hydrogen's happy, so it's not going to get any more electrons. It only has that first energy level. So we have 4. We need 6 more. So 1, 2, 3, 4, 5. And that 6th one we're going to put on nitrogen because nitrogen normally has a lone pair anyways. So that's how we chose where that other electron goes. And now we take a look. Hydrogen's happy. It has 2. Carbon only has 6, so it needs 2 more. Nitrogen only has 6. It needs 2 more. So what they're going to do is they're going to share these bonding electrons that are left out. And so they each share another 2, and we end up with an H, C, and then 3 bonding pairs of electrons, and then our nitrogen at the other end. Don't forget it has 1 lone pair. And so there's a Lewis structure for hydrogen cyanide. So for ethane, here we have 2 carbons plus 6 hydrogens. In terms of electrons, we have 2 times 4 electrons for the carbons plus 6 times 1 electron for the hydrogens, which is going to leave us with 2 times 4 is 8 plus 6, 14 electrons. In terms of atoms, we have carbon and we have hydrogen. Carbon is going to be our most electron deficient. So carbon is going to be our center. To it we're going to bind a carbon. And then around the other 3 spots we can put hydrogens. Now that's only 3 hydrogens. We need 6. Luckily for us, the other carbon has a whole bunch of spots to bond to, so we're going to put 3 more around that, and we're going to put bonding electrons between all of them. There we go. If we add up our electrons, we have 1, 2, 3. We have 2, 4, 6, 8, 10, 12, 14. So we have all the electrons that we need. All of our hydrogens have 2 electrons in their valence shell, so they're happy. Our carbons all have 8, so they're happy. So we have a good Lewis structure. So I'll just write it once more without all the gobbledygook in the way. And here is a reasonable structure for ethane. So here's just another example of how it's done. You want to get your electrons counted. You draw your atoms. You pick the one that's the most electron deficient for your center. So again, this one would be carbon. And you start bonding things around it. Sometimes you have more than one center, and that's okay. Here we have a carbon center that bonded to some hydrogens and some oxygens. Here we have an oxygen center bonded to a carbon and a hydrogen. Notice that oxygen has those 2 lone pairs. And then just check, make sure everybody has a full valence electron energy level. If they do, then you have a good structure for your atom. You make sure you have the right number of electrons, and that's about it. Now, Lewis structures are fine, but they're kind of sloppy and they're kind of messy, so we often replace them with structural formulas. And what structural formulas are is they simplify the Lewis structure while still conveying the same information. So first we still find the Lewis structure. It's important to always find that Lewis structure so that you know how those atoms are bonded together. once you have your Lewis structure, all of your bonding electrons are going to be represented by straight lines between the atoms, and your lone pairs are no longer drawn. So that's the part of the information that goes missing. Just a reminder that these structural formulas still don't represent shape. We're drawing two-dimensional images of three-dimensional molecules, so we aren't conveying shape with a structural formula. And so here's a couple of examples of what equivalence formulas would be. Notice that the chlorine has 3 lone pairs here. They're not drawn on the structural formula. And the bonding electrons, so here's 2 bonding electrons, they're represented by a straight line. So the straight lines between atoms represent 2 electrons. For methanol, same idea. That hydrogen on the end there beside the O can be represented off the end, or if you wanted, you could draw it this way. Because these pictures don't represent shape, either is acceptable, or you could, if you wanted, draw it off this way. Any of those 3 choices would be fine. For formaldehyde, again, since there are 2 sets of electrons being shared, we draw 2 lines. These 2 lines represent 4 electrons. So we'll draw the structural formula for water. Now we've already drawn water's Lewis structure, but we'll draw it again using our method. So we have 2 H's plus 1 O. So 2 times 1 electron plus 1 times 6 electrons. So we're going to have 10 electrons. If we take a look at our atoms, oxygen is missing 2 electrons. Hydrogens are only missing 1 electron, so we're going to start with our O as our center. So we go O, 1 hydrogen bonded to it, another hydrogen bonded to it, and then we fill in the spots. Oh, and I made a mistake there. Look at that. 1 O. 6 plus 2 is 8 electrons. There we go. So 8 electrons. There's our Lewis structure for water. Alright, so structural formula for difluorine monoxide. So before we can draw it, we have to know what it looks like. Difluorine means Fl2, monoxide is O1. So there is our structure, or our formula for difluorine monoxide. In terms of electrons, we have 2 Fls plus 1 O. Fluorines have 7 valence electrons, so 2 times 7 plus 1 times 6. So we have 20 electrons. Fluorine, and look at that. Sorry about that. We're going to just go fluorine's chemical symbol is just F. Holy, okay, 2 F's plus an O, which means we're going to have 14 plus 6, and so we're going to have 20. The rest of it was right, but wrong chemical symbol. No marks for me. Okay, so fluorine has 7 valence electrons. Oxygen has 6 valence electrons. And so oxygen is the most electron deficient, so it's going to be our center. And we're going to bond fluorine and another fluorine to our oxygens. To our oxygen. And then we put in our bonds. Then we fill in the rest of our electrons. We need 20. We have 4 right now. 5 including the one I cheated with here, but there's 4. 5, 6, 7, 8, 9, 10, 11, 12. So now all of our orbitals have 1 electron. We can start going in and pairing them up. So that was 12, 13, 14, 15, 16, 17, 18, 19, 20. All of our orbitals now have 2 electrons. All of our atoms are now surrounded by 8 electrons, so we have a decent structure for, or our Lewis structure. for our difluorine monoxide. Now we're going to make a structural formula. We can drop the lone pairs, and bonding electrons are represented by straight lines. And there is our structural formula. We'll draw another structural formula here, HOCN. So we have a few atoms here. And so we're going to go with, we have 1H plus 1O plus 1C plus 1N. So now we're going to count the electrons. We have 1 from the hydrogen, plus 6 from oxygen, plus 4 from carbon, plus 5 from nitrogen. We only have 1 of each, and so we should get a total of 16 electrons. Again, we're going to draw our atoms out. We have a hydrogen, we have an oxygen, we have a carbon, and we have a nitrogen. The most electron deficient is carbon. It needs 4. So that's going to be our center. So we'll put our carbon down, and we'll bond our other atoms to that. So N on one side, O on another side, H, and then we start putting in our bonding electrons. And now we go around and we add the rest. So we have 6, we need another 10, and we go around. Remember, hydrogen can't take any because it's already happy. So 1, 2, 3, 4, 5, 6, 7. So that's 7. Now I'm going to start doing lone pairs, and normally carbon doesn't have one. So 7, 8, 9, 10, 11, 12, 13, 14. And now we have a problem. We still have to put 2 more electrons in there, and we have nowhere to put them. So because of that, we say, well, you know what? This probably isn't a very good Lewis structure. So that's probably not what the molecule looks like. So we start over again. We still want carbon to be our center, and we're going to bond nitrogen to one side and oxygen to one side. And now I'm going to say, well, you know, oftentimes when this H and O are in the same compound, they're bonded to each other. So I'm going to put the hydrogen onto that oxygen as a second center. And now we'll start filling in our bonds. And we have all of our bonding electrons in, and now we'll put in the rest. So that's 6, 7, 8, 9, 10, 11, 12, 13, and now we'll start doubling them up. 14, 15, 16. And the reason I put it here is because nitrogen normally has that lone pair. So because of that, I gave that electron to nitrogen, and now I can see that, well, I have all 16 electrons, but I have some unbonded electrons here, some bonding electrons, and if I start sharing them, carbon needs 2 more. It only has 6. So if it shares 2, and if nitrogen shares 2, then they will both have 8. So I'll just draw it out in a linear fashion here. Here's H, and here's where you can see the value of structural formulas, because things start to get a little messy. Like that. And so for the structural formula, there's our Lewis structure. For the structural formula, we can say, well, there's a bonding pair between H and O, a bonding pair between O and C, 3 bonding pairs between C and N, and there is our structural formula. So there's the homework. Just to note, the practice problems, their solutions are in the textbook, and the solutions start on page 728.